Okay, we're going to now actually implement spectral methods. In fact, we're going to implement the FFT to solve the shallow water equations. And what you'll see is how efficient and nice you can do very sophisticated things with these spectral techniques. So again, the FFT method will implement this fully and show you some of the tricks of what you need to do, especially as you're going to 2 dimensions in this shallow water wave equations. So I like this example because it's pretty sophisticated, and yet it gets us to all the key ideas we need to do, be thinking about when we solve these this kind of equations. So I want to first talk about the spectral implementation. For instance, here is a PDE that has a linear component and a nonlinear component. And so one thing that we can do with this is we can transform this, and we're going to turn this into a system of ODEs. So when I transform this, notice that the linear part gives me a decoupled set of ODEs, and all the mixing that happens here is in the nonlinear domain. So I'm going to have to march this forward in time, and it's really important that you understand, and by the way, the linear term alpha k came from just, if I had a linear operator L, if I Fourier transform it, I can just look at these coefficients A, B, and C. The Fourier transform of the second derivative gives you negative k squared, the first derivative ik, and so forth. And so this is what this alpha k is, okay? So it's the linear parts that you can transform. And I want to march this OD forward in time. But notice, when I step forward in time in the Fourier domain, I now have an updated state of the system in the Fourier domain. But now I have to come back to my regular domain, U, and I need to do that because every step I take, I have to update this nonlinearity. Notice that if it weren't for the nonlinearity, if this was gone, I could just simply stay in the Fourier domain. But this one here, to evaluate it, I have to know what U is. In other words, if I take a step forward, I have to come back to U, I have to compute the nonlinearity and then re-Fourier transform it. So understand that when you do this implementation, you have to come into the Fourier domain, out of the Fourier domain, into the Fourier domain, out of the Fourier domain, at every single time steps delta t. So your right-hand side function, when you're solving this, is involving you coming in and out of the Fourier domain. Okay? And coming in and out of the Fourier domain is an n log n operation. Okay? So just keep that in mind. Lots of Fourier transforming. Okay, so let's go to the 2D shallow water wave equations. We're going to solve this completely. You're going to have a little movie of this, or at least I'm going to show you some snapshots of what we're going to do here. So it comes in 2 pieces, and we've already talked about discretization of this model. So here's where the time evolution comes. So we're going to march forward the vorticity, which is coupled to the stream function. And here's the stream function vorticity coupling in the derivative relationships with a little bit of the Laplacian on that vorticity. In other words, a little diffusion. The stream function itself satisfies this Poisson equation. So I have the stream function, and the Laplacian is equal to the vorticity. So the first step is given an initial vorticity, I'm going to have to solve for the stream function, and then I can take a step forward in time here. And once I've done that, I can come back with my updated vorticity, solve for the stream function, come back, solve this again. This is the most expensive piece right here. Because remember before, when we showed the discretization and arranging of the data, this was an AX equal to B. But now I'm going to solve this all in the Fourier domain. So now this is going to be as fast, it's going to be at n log n speed versus when I did the matrices, it's going to cost me sort of in some sense generically order n cubed or order n squared. Okay, so let's go about solving this. So first of all, let me define a time range. We're going to run this through and solve it from 0 to 10. We are going to pick a diffusion value that's very small. We're going to define our domain sizes, which are 20 and 20, number of Fourier modes in each direction, and usually these are picked as powers of 2. So remember that the Fourier domain takes a problem size n, 2 problem size n over 2, 4 problem size n over 4. So typically the way you pick the discretization, it's a power of 2. That's no longer really required with Fourier transforms because they have very sophisticated padding methods. But oftentimes, just historically, if you use Fourier transforms, you pick 64 points, 128 points, 256, 512, 1024, 2048, and so forth. In other words, powers of 2. So here, I'm going to do 64 just to sort of demonstrate this. And my total size of how I'm going to arrange my data that's two-dimensional is nx times ny. Okay? So it's 64 squared is the state space. That's my two-dimensional problem. Next, what we're going to do is define the x domain, which goes from negative L of x to L of x over 2, L of x over 2 to L of x over 2 in n of x plus 1 points. Remember, periodic boundary conditions, so I define n plus 1 points, and I only take the first 1 through n. Same thing with the y domain, and then I mesh grid them. So this capital X, capital Y, now are two-dimensional coordinate systems, x, y. Okay? Once I have that, because I'm in the mesh grid domain, so it knows that it's two-dimensional, so mesh grid makes it two-dimensional, I now define my initial condition. Here it is. It's going to just be essentially an elliptic Gaussian function that we're going to have here that we're going to evolve forward in time. Okay? So that's what we have here is our initial condition and our setup for our domain. So now, other things we have to set up. We are using a Fourier transform, which means when we take derivatives, we have to multiply by ik. So we're going to go ahead and go into the Fourier domain and define these ik's. So here's what it does. So first of all, remember the Fourier transform believes you're working on a 2 pi periodic domain. But we are actually on a domain that's L of x and L of y. So here's the rescalings. The 2 pi over L of x and 2 pi L of y are the rescaling to say, oh, you're now going to be on a 2 pi periodic domain. And here are your wave numbers. Remember, there is this butterfly algorithm. So your wave numbers, which you go from negative n over 2 to n over 2, are now flipped. So it goes from 0 to n over 2 and minus n over 2 to 1. And that's what this does here. It already knows that when I take the Fourier transform, I'm going to be in this flipped domain. And so we're making the wave numbers to be set up for that. We have the k of x, we have the k of y, and just like before, we mesh grid both of them. And then we can make this matrix here, which is kx squared plus ky squared. Okay? So that's going to be the Laplacian. Remember, there's 2 derivatives in x, 2 derivatives in y. So we're going to have that, instead of keep recomputing those matrix inner products in the right-hand side, we can do it once outside of the loop, and we're in a much better place. Less computing at that point. Okay? Because when we solve for the stream function, remember the stream function solution is I Fourier transform the vorticity, divide by kx squared plus ky squared, which is this here, and then I come back. The other thing we do here right away is, remember, we have a divide by 0 problem unless I just simply say take the first component, the 0th component, which is supposed to be 0, and make it 10 to the minus 6. So I've already taken care of what would have been the divide by 0 issue that we talked about in this problem many lectures ago. So that's the setup for the wave numbers. So I have the spatial domain set with an initial condition. I have the wave number set. We are now ready to proceed along. By the way, all this code is on my GitHub, so you can just download it and run it, and this will produce for you the movies or the observations we're going to see. And now we call the right-hand side. So what are we going to do on the right-hand side? So first of all, we're going to come into this domain. And the way this is going to work, by the way, is if we go back here, when we produce the initial conditions, when we send in initial data and these steppers, we're going to actually send in the data here organized in terms of its real and imaginary parts. So the way that we send in the data is you can't send in complex data into this right-hand side, at least from the stepper I'm using. You have to then send in the real part and imaginary part. So the first thing I do is glue them together. And there we go. That is our vorticity in the vector space. I now reshape it back to the original XY type coordinate system. So this isn't, remember, in the Fourier domain. I sent this in the Fourier domain because we're stepping in the Fourier domain. So I've sent it into the Fourier domain. And the first thing I do is right here. I solve for the stream function, which means I take the vorticity, which is Fourier transformed in x and y. I divide by kx squared plus ky squared, which is right here, and there's a minus sign. I now have the stream function in the Fourier domain. Okay? And so now what I can compute is, if I want to compute all I need from the stream function is its x derivative and y derivative. It's already in the Fourier domain, so all I have to do to get the x derivative is multiply by ikx. And all I have to do to get its derivative in the y direction is multiply iky. So here we go. And once I do that, I can inverse Fourier transform it, and now I have psi of x and psi of y. So that's great. So I've got those derivatives computed. You see how efficient this code is. It's so small. I'm solving a pretty interesting problem that's hard very compactly. And by the way, I still need a derivative of omega. So I need omega x, omega y. And again, same thing. Just take its Fourier domain, multiply it by ikx, iky. That gives me one derivative in x, one derivative in y. And the full right-hand side is this diffusion term. It's minus nu times k. And k, remember, is kx squared plus ky squared, so that's 2 derivatives in x, 2 derivatives in y, times omega. And then the Fourier transform, and this is the nonlinear term. So I had to bring all these back out to the real domain in order to compute the Fourier transform of this nonlinear term, which is the x derivative of the vorticity times the y derivative of the stream function minus the y derivative of the vorticity times the x derivative of the stream function. And so I take the FFT of this, then I reshape it back up into the vector space, and this is the entire right-hand side that we have available to us. So this little bit here is really important for you to understand. And it's so powerful because I've solved now, these equations here very compactly. I solve for the stream function, and then I update this with these formulas here. And all of this is encoded in this many lines of code right here. So a lot of heavy lifting. I'm coming in and out of the Fourier domain, and I'm marching forward, a vector space, even though this is a two-dimensional system, which lives sort of in this, in a square xy square. I'm coming in and out of this space. I'm making a vector, but I'm also in and out of the Fourier domain as well. So, and by the way, the 2D Fourier transforms right there, IFFT2, FFT2, and so these are how you would take two-dimensional Fourier transforms. And final piece is you just run it, by the way. And by the way, here's how we went into this thing. When we took the data, we sent in the real imaginary part, and we just basically call this OD solver. You call the right-hand side, send in your initial condition, send in the time span, send in all these parameters that you want to use. You're there, and then you can make a movie at the end of this thing. And here's what the movie looks like. So I send in this elliptic vorticity, and here's what it looks like. It looks like a little hurricane, which is exactly what it should look like. This is 2D shallow water waves equations. So whenever you look at hurricane season, you'll see these hurricanes like this, because it's 2D shallow water approximately in those equations. And so that's the kind of behavior that you get out of here. And what I've shown you is a way to solve this extremely fast, extremely accurate, using spectral methods the whole way through. You're using the power of the FFT, and notice for this simulation I can get away with periodic boundary conditions. And so that's the advantage, because now I can just use the FFT for this. And if this vortex was moving across the domain, it would just show up on the other side. After it gets out of one side, it comes back on the other side. So that is a spectral implementation code that's on the GitHub. You can download it, play with it. I would say this is sort of this, this code in particular kind of sets up a framework for you of sophistication. This is a non-trivial, it's not so easy. It's not like solving the heat equation. Nobody's impressed if you solve the heat equation, right? It's too easy because you can just write down the solution. Here's this first model that involves multiple pieces put together in a way, and it produces really interesting dynamics that starts to get into why we have computers in the first place, because I can't do analytic solutions, but I want to see some of the physics that comes out of this. And so here's a model that really starts to test, in some sense, your skill set in terms of solving realistic problems. So again, this is a spectral method implementation using the FFT. I think one of the big educational pieces here is for you to dive down into that code, really understand the pieces, because if you understand this code, you will I think you'll find that you've taken a big step forward in learning how to compute and learning how to use spectral methods for solving this. They're faster and more accurate than what we did previously, which is to use finite differences.